Hello all. Today let we learn about the other logical operations in Boolean algebra and logical gates. In last class we have learned about the logical gates of two input and more than two input, basic gates, universal gates and special gates. And we have discussed about their logical truth tables, their Boolean expressions, what are their logical symbols. Today's session, if we have taken those three operations of basic operations of your logical gates, which are AND, OR and NOT, with the use of these three operations and using only two variables, we can implement total number of functions which are 16. So if your number of input variables are n, then we can obtain total number of functions from that n input variables are 2 power 2 power n. For example, if I replace the number of input variables with 2, then 2 power 4, it becomes 16 possible logical functions we can implement using your two variables additionally with the three logical operations. The same manner, if n is replaced, your input variables are replaced with the three variables, then your 2 power 8 become 256 possible logical functions we can implement it. So using only that three variables and additional logical operations of three basic operations. So if I'm going to implement 256 possible logical functions, so what will be our output Boolean expression of each expression we have to learn. So let me first take with a two variable and using your three Boolean expression or Boolean functions of your AND, OR and logical gates. Then we will implement these 16 Boolean functions, how it is obtained. So F naught is a logical zero, the initial output function, where for all the input variables of possible 0 and possible logical 1 we replaced here. So F naught will give you the logical 0. So for each combination you are getting your output which is 0. Hence it is defined as a logical 0 function. Next, now we have replaced this we have represented all the 16 possible functions which has started with the label of F0 to F15 function. As here we have four combinations and we replaced for each combination the output functional value with the 1 bit. So then we obtain the 4 bits. So for a 4 bit the possible combinations are 16 possible combinations. So we replaced that each unique combination started with 000 to 1111. So we have replaced these functional values. F0 is taken as 000, F1 is taken as 001, F2 is taken as 0010. So F3 is taken as a binary 3, F4 is taken as 0100, F5 is 0101, F6 is 0110. So like this, so we have replaced that four output functional values with the possible zeros and ones. So total 16 combination we obtained. Now, so we can derive each output function, how we are obtaining the Boolean expression of each function using your truth table form. So now we need to get that F0 is a logical zero function, F1 is an AND operation between the two variables, F2 is an AND operation between the two variables, but here the second variable is a complemented. So it's a AND operation between the first variable and the complement of the second variable. F3 is X, which is transparent to the first input variable, which will transfer your first input variable that was taken as a F3 output function. F4 is also a AND operation between the complemented first variable and its second variable. Fy is also a second variable transfer, or it is transferred to the second variable, so which will transfer your second variable. F6 is an exclusive OR operation between your first and second variable. F7 is a simple OR operation between the x and y. F8 is a NOR operation. F9 is an exclusive NOR operation, and F10 is complement of your y. F11 is an OR operation between x and y, complement of y. F12 is complement of your first variable, which is x, so x bar. F13 is it's an OR operation between the first complemented variable and second variable. F14 is a NAND operation. F15 is a binary logical one. Now, so let me derive each output function, so using your truth table form. So F naught will give you the logical zero, since for the each possible inputs of zeros and ones on x and y, it would give you the logical zero function. Hence, it is defined as a logical zero function. F1 is for 0 0, it is 0 0 1, it is 0 1 0, it is 0 1 1, it is 1. The functional value is 1 only when x is 1 and y is 1. So if I have taken that as a product term, x y will resembles an AND operation between the first and second variable. So F1 implements an AND operation between the first and second variable. Next, F2 is having one functional value is 1 only for a combination where x value is 1, y value is 0. So if I mention that as a product term, so then it gives you the F2 functional value is x and of y bar. So here an AND operation between the first variable and its complement variable of second. So F3 is having the two functional values are 1 1 for a combination of x is 1, y is 0. So hence we mentioned here x without complement, y is represented with the complement as a product term. So next, second functional value is 1 for a combination of x is 1 and y value is 1. So we mentioned as a product term without complements x and y. So from this two product term, let I take x as common, then I have a sum term of y bar or of y. So now y bar or of y using OR laws. So if you are ORing a variable with its complement, always it is replaced with a logical one. So now if I minimize that, then it will transfer your the first variable as your output function of your F3. So now if I observe that, I can easily recognize using the truth table. So for all the possible four combination, F3 value is as like as your x value. So first is x value 0 0. In this x value 0, F3 value is also 0. In second combination, xy value are 0 1, where F3 is equivalent to that of your x. Next, third combination, xy value are 1 0, but F3 follows your x value. So since that, so it is equal to logical 1. So for a last combination of 1 1, so F3 follows your input input x. So it's also equal to F3 is equal to x. So next, F4 is having a functional value 1 only for a combination where x value is 0 and y value is 1. So now if I have taken as an AND operation, then it would be giving your product of your complement of first variable and its second variable. Next, F5 having a two functional values for a such combination of x is 0, y is 1, x value 1, y is 1. So if I have taken that as a product terms, so we have two product terms in our equation. So x bar y or of xy. So from these two product terms, so let I take your y as the common variable, then I could get x bar or of x. So using OR laws, if I replace x bar or of x, we can have your y. So F5 is transparent like your y value. So it will transfer the y value. So F6 is having the two functional value for a combination 0, 1 of your xy, 1, 0 of your xy. So now we write that as a product term x bar y or of xy bar. So it resembles special function which is an exclusive OR operation between your x and y. Now F7 is 0, 1, 1. Here we observed three functional values are 1 for a combination of 0 1 1 0 1 1. So if we write that as a product term, so x bar y or of xy bar or of xy. So now from the first and the third product term, take y as common, then here x bar or of x or of xy bar. So now x bar or of x is replaced with logical one and or of xy bar. So using your distributive law. So y or of x, y or of y bar. So as y or of y bar is 1, so now x or of y and of 1 become x or of y. So it gives you the OR operation between the first two variables x, y. So F8 is having only one functional value for a combination where x and y are logical 0. So now let me write this as a product term x bar and of y bar. So it gives you the resemblance on your De Morgan's law. So and of two complementary variables which is equal to the OR of your complement of your OR of the first two variables. F9 having a two functional values are 1 for 0 0 as well as for 1 1 on your xy. It resembles the exclusive NOR operation. So now we replace that x bar y bar or of xy with exclusive NOR of y, or it is equal to the complement of your x exclusive OR of y. Next F10 is having a functional value 1 and 1 for 1 0. So now it is having two product terms as x bar y bar or of x y bar. So from this two product term, let I take y bar as common, x bar or of x is replaced with logical one, then it would give you the complement of your y bar. So y variable or your second variable. So almost for 0 you are getting 1 1, you are getting 0 0, you are getting 1, your 1, you are getting your 0. So it will transfer the complemented second input variable as the F10 function. F11 is having three functional values are logical one for a product terms of x bar y bar or of xy bar or of xy. So now we wrote those three product terms, and from your first and second term, let me take y bar as common, then here we have x bar or of x or of xy. So x bar or of x is replaced with logic 1, hence here we have only y bar and or of xy. So using your distributive law, so let me distribute this complemented variable with x and y. So we obtain x or of y bar and of y or of y bar. As y or of y bar is replaced with 1, so it will give you the OR operation between the first variable and its complemented second variable. So next F12 is having the two functional value for 0 0 and 0 1. So x bar y bar or of x bar y. So from these two terms x bar is taken as common, y bar or of y is replaced with logical one. Now F12 implement the complement of your, so it will transfer the complement of your first variable x. So next F13 gives you the three output functional values for combination 0 0 0 1 1 1. So now 0 0 is replaced with x bar y bar as a product term. So 0 1 is replaced with x bar y and 1 1 is replaced with xy. So now we obtain here upon simplifying your equation. So x bar is taken as common from your first two terms. Y bar or of y is replaced with 1, and using your distributive law x bar or of x and of x bar or of y. So x bar or of x is replaced with logical one, then we obtain here x bar or of y. So which is an OR operation between your complementary variable of first variable and the second variable. Now F14 is x bar y bar or of x bar y or of xy bar. So now upon taking the common variable, then we obtain the NAND operation between XY. F15 for all the possible functional values, you are obtaining a logical one. So this is about our other logical operation. Next class we are going to study about your minimization